All right, today we're going to talk about solid types and solid properties. We sort of alluded to this last time, but let's just go over this formally, and it wouldn't hurt to go over it again. So, anytime you have a solid in chemistry, we generally refer to solids as crystalline solids. Oops. Crystalline solids. And it helps if you have a pencil that is recognized. Hang on a second. Okay. So, crystalline solids are highly organized particles, right? And in any repeating, you can tell, like in an ionic solid, which we saw before, there is a pattern here. It's very clear and it's repeating. The term we use for this is called a lattice. That's a term that kind of pop up here and there. And we differentiate a highly organized solid versus what's called amorphous. An amorphous solid is unorganized. Think like silly putty, right? That's a solid, but an amorphous solid is sometimes called a semi-solid, right? So you can make a case for silly putty being like a liquid because it can take the shape of its container, right? But really, it's a semi-solid. Anyways, we're only paying attention to crystalline solids, which are organized. So in an ionic crystal, we know that ionic compounds are made up of positive and negative ions. Remember the terms for these? What do you call a positive ion? Right, a cation. And the negative ions are called anions. Right? Each one of these is called a lattice site, a place where an ion is found. The ionic crystal has attractions between oppositely charged particles, oppositely charged ions, and that should make sense because positive and negative attract, right? So, properties. Ionic crystals are hard. You saw that in lab. They are brittle and have high melting points. They are non-conductors as solids, but they do conduct as liquids. So when you dissolve the salt in the water solution conducted. Examples of ionic compounds would be anything that has a metal with a nonmetal or a metal with a polyatomic ion. So let's talk a little bit about these being brittle here. I'm going to add a page here so I can draw a better picture. Okay, so your typical ionic solid looks like this. And the word brittle means something that shatters, right? So the thing is, right now, when you look at an ionic solid, you have attractions. Wherever I have this yellow highlighter, that's an attraction. And that attraction should make sense because you have a oppositely charged ion. Attractions between ions. And they're basically everywhere. So, when you hit this with some kind of force, let me duplicate this. So let's say we hit this with some kind of tiny little hammer. Bam, right there. The effect of that is that these will all get shifted downward, which ends up looking like this. Oops. We go from a state of having maximum attraction to maximum repulsion in a split second, because this row of ions that was aligned is now pushed out of alignment. So 1 second, they're really attracted, and a second later, they're really, really repelling, and therefore it's going to fly apart. So that's why it's brittle. It's kind of a unique characteristic to ionic compounds, right? The fact that you can go from maximally attracted to maximally repelling so quickly. Okay. So let's now talk about the second type of solid, molecular crystals. Remember when we say the word molecular, well, molecular means made up of molecules. And if it's made up of molecules, that means it must be all covalently bonded. Right? So in other words, the intramolecular forces are covalent bonds. Right? So intra are covalent. But what actually holds the solid together are the IMAs, the intermolecular. Dipole-dipole, London forces, hydrogen bonding. So, how is it that these molecular structures are arranged? All right, I'm going to move up here and kind of draw a picture. So, there's really two types of molecular solids. You can have the nonpolar type, or you can have the polar type. And so let's discuss each. For the nonpolar type of solids, your molecules are all nonpolar molecules. And when a molecule is nonpolar, it only has one type of attraction. Who remembers what type that is? What intermolecular attraction holds these guys together? You had a list, you had a homework with a list, and you had to categorize them into 6 different columns.
London forces?
Yeah, these are, yes, correct, London forces. So London forces hold together these molecules. Now, how do you categorize London forces, strong or weak? In the scheme of intermolecular attractions. They are weak, yeah. So, because they are weak, molecular solids are soft and have low melting points. Now let's go back and draw a picture of polar solids. All right, so when you have a molecular solid, when it's polar, we mean that the molecules have asymmetrical electron distribution. And this is where we use delta negative, delta positive. And the arrangement of these delta charges have to make sense. The partially positive sides attract partially negative sides. The partially negative sides attract partially positive sides, and so on. And we don't have to fill out all of these. Just draw enough in here so you get an example. So the attractions that are taking place here, 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 here. Right? There's lots of attractions taking place. What's the attraction responsible for holding polar molecules together? Yeah, Carson?
Dipole.
Yeah, these are dipole-dipole, correct. Now, in a polar substance, not only does it have dipole-dipole, but because it is a molecule with electrons, these also have dispersion forces. And that's important to remember, okay? So when you have polar molecules, not only are they held together by dipole-dipole, but they are also held together by dispersion forces. So it's like two attractive forces operating at the same time. Now, there's another type of polar attraction, but it's highly specified. And hydrogen bonding looks a lot like these polar molecular solids. The difference is that their strength of the dipole-dipole attraction is much greater. So remember that we do our delta charges.
Excuse me, I think I left my iPad. Yeah. Thank you.
Okay, so delta negative, delta negative. What I'm trying to do here is draw these partial charges larger because the partial charges in hydrogen bonding is greater than the attraction in dipole-dipole. So, oops. Okay, now hydrogen bonding, remember we said there's two criteria for hydrogen bonding to happen. They had to be polar molecules, but they also had to have H directly on F, O, or N. But here's some tips, right? Oftentimes you'll see a formula, and the formula will be like, C4, H9, and there will be an OH, just kind of conspicuously placed at the end. That OH there, that makes this what's called an alcohol, and alcohols all have hydrogen bonding. So if you see a formula like this, that's H bonding. Other examples, sugars. You know of sucrose, but there's lots of sugars. There's fructose, glucose, galactose, lactose. And in general, a sugar has twice as many hydrogens as carbon, but it has about the same number of oxygens as carbon. So you just have to recognize the formula when you see them. Okay? It's going to have lots of hydrogens. It's going to have twice as many hydrogens as the carbons, but it's going to have just as many oxygens as the carbons. Those all have hydrogen bonding. In fact, they have a lot of hydrogen bonding, which is why all sugars are solids at room temperature. Whereas liquids, alcohols are liquids. Why is a sugar a solid at room temperature, but why is an alcohol a liquid at room temperature? Well, it's because sugars have way more hydrogen bonding than alcohols. Does that make sense, right? Hydrogen bonding is like the strongest attraction between covalently bonded molecules. So the more of it you can have, the more solid it's going to be. Okay. So here's an example of I don't know if you've ever done this before. You guys ever make rock candy? Right, where you take a pot of water and you get boiling, and you dump as much sugar as you can possibly dissolve in that boiling water, and then you let it cool, and you dangle a string in it, and then the excess sugars crystallize onto the string. This is all just sugar, table sugar, right? And table sugar, it's hard, but you could crush it pretty easily with like a spoon, right? Or a book or a cup or something, right? It's not like it's metal, right? Okay, so how do you recognize something if it's molecular? Well, they're made up of all nonmetals, right? The formula's all nonmetals. Means it's molecular and covalently bonded. Okay. Now, just to clarify, if something is covalently bonded, it doesn't mean it has to be a solid. It just means that the solids that are covalently bonded are softer, right? Because water is covalently bonded, right? There's lots gases, right? CO2, right? Oxygen, all of those are covalently bonded. Well, those aren't solids. I'm just saying that molecular solids, if they are crystals, they're not very strong. They're not very held together very strong as a solid is compared to like ionic. So don't have to be solids if it's molecular. All right. Next, we're going to talk about something called network covalent. And this is weird, right? Because it has the word covalent in it. But here's what's going on. So diamond, you've often heard of diamond as being, the hardest substance on Earth, right? So diamond, it looks like this, where each one of these is a carbon atom, right? Every single one of these is a carbon atom. If I kind of retrace one of these, you should see something that's familiar. Actually, that's not a good color. Let me get some brighter. Does that shape look familiar? What shape is that? That's a tetrahedral. Now, these bonds here, these are all covalent bonds. And remember, a covalent bond is what we call an intramolecular force. Do you remember when we compared intra versus inter? Which one is stronger? Intra. A diamond has only intramolecular bonding. There's actually no intermolecular bonding. It's all intra, which means every single one of these atoms are directly covalently bonded with all of its neighbors. So all carbon atoms directly covalently bonded. So that's this. This is the model of diamond. There's no anything that has this many direct covalent bonds is going to be the strongest material that there is. It's the reason why it's called network covalent is because it's literally a mesh, a network. Right? There's nothing weak holding this structure together. It's only covalent bonds in every direction. Every carbon can make 4 bonds. Every carbon is making 4 bonds, except, the ones on the end. Okay? So, what do we use diamond for? Well, they stick diamonds on drill bits to bore through bedrock in the earth, to drill through mountains so they can build a tunnel, so they can put a train going through a mountain, right? Why diamonds? Because diamonds are harder than any other substance. Like, you wouldn't be able to cut through a mountain and all that rock with, a regular metal drill, because what would happen is the metals will soften over time and then it won't be as sharp anymore. You guys know, like, kitchen knives dull over time. That's why a lot of kitchen knife sets have sharpeners, right? Metals will dull over time. That doesn't happen to diamond. Okay, so diamond and really anything that is network covalent is the hardest substance there is. Now, if they're that strongly attracted, then it's really hard to get these to loosen up and separate. Meaning it's really, really hard to melt it. Very high melting points. When I say very high, I'm talking like greater than 1,000 degrees Celsius. 1,200 degrees Celsius, 1,400 degrees Celsius. Thousands of degrees Celsius. That's what I'm talking about. We cannot melt anything that is network covalent here in this lab. We can't. We don't have anything that gets that hot, right? Most of them are non-conductors, all right? With the exception, the two that are silicon and graphite. And those are actually important industrially. Graphite is what we use in pencils, right? It's also used as a lubricant in machines. And silicon is microchips. It's important that they conduct, because in your computer, in your phone, in your iPad, like, you need chips that conduct in order for them to work properly. So let's talk about graphite then, since we're here on the topic. Take a look at that picture. In graphite, if you look at it from the top down, do you see how these carbon atoms are bonded, but each carbon atom does not have 4 bonds? How many does each carbon have? 3. Okay, well, 3 is less than 4. And when something makes 3 bonds, it's planar. It's flat. So this sheet of carbon atoms is directly covalently bonded, like these sheets here. These are all bonded to each other. But the problem is these sheets are not directly covalently bonded to each other. Instead, they are held together by weak dispersion forces. So graphite is not strong. Graphite's pretty weak. If this represented the tip of a pencil, if you just pushed this down on paper and dragged it across the surface of a paper, these layers of carbon, of graphite, would just come right off and leave a trail of graphite across the paper, and that's actually how you write with a pencil. It breaks very easily, right? Have you ever, tried to advance the lead on your pencil, but you advance it too long and you start writing and you snap off the tip, right? That has to happen if you have a mechanical pencil. It's just like a law, right? That'll happen at least once. Okay, so what is the difference then? Why is diamond the hardest substance on Earth, but why is graphite not hard at all? It's because of this difference. This network in diamond is what's called a 3D network, whereas the network in graphite is a 2D network. And that makes all the difference. All right, so this network covalent bonding happens in other substances besides just carbon. It also happens in silicon, like when silicon is by itself. It happens in silicon dioxide, which is SiO2. We talked about this a little bit before. This is called quartz. Sand, by the way, is quartz. Sand is silicon dioxide. But when you step on sand, you don't typically think of it as hard, right? Why? It's like powderized, right? It's tiny. That doesn't hurt you. But if you were to walk on like an actual chunk of quartz the size of, boulders, you would not want to walk on that barefoot, right? It would tear up your feet, right? Combinations of silicon, carbon, tungsten, and boron. So any two combined between these elements. So carbon boride, silicon carbide, tungsten carbide, etc. Any combination of those, they will network covalent bond. This is tungsten carbide. This is one, it's network covalent, and it's extremely hard. We'll just pass it around if you want to feel it. Like, you cannot, like, you wouldn't want to scrape yourself on this. You would not want to lean up against it, because it would just cut you to shreds. Okay. So, are we okay with network covalent, guys? What is the takeaway from network covalent? What did I highlight on here that you should know for sure? Very, very hard and very, very, very high melting point, right? Okay. And you should know why. And here's the why, right? The 3D network, right? All the interconnected intramolecular covalent bonds. Right? Here's a picture of a diamond. You've seen pictures of diamonds before. Here's a picture of a pencil tip, which you've seen before. All right, then. Let's talk about the last type of solid, which is metals. Metals have what's called metallic bonding. And metals are weird. The thing about metals is that you have to remember that metals have low attractions for electrons. Remember that? Low ionization energies. If I said, what's the easiest element to take an electron away from, you should say a metal, specifically an alkali metal. Right? So, because of that, when you have a solid metal, this is actually what's happening here. You can put it here. That's fine. These electrons right here, these are the valence electrons. And the thing about valence electrons in metals is that they are what's called delocalized or non-localized. What that means is they don't stay put. They do not belong to a single atom. They're community electrons. They're shared. So every single one of these electrons travels and moves throughout the solid, always moving. Now, at any given time, like in this picture here, how many metal atoms do we see here? There's 5 times 5 rows. So there's 25 pictures of atoms here. If there's 25 atoms, there should be 25 electrons, 25 valence electrons that are moving. Let's say this is sodium, for example. There are 25 valence electrons, but because they're always moving, you can't just assign a valence electron to any one specific atom. They're all freely shared, right? Like you go to gym class, there's 10 of you, there's going to be a bin of 10 basketballs, and your gym teacher's going to say, go shoot around, right? And then the next period comes in, you leave, 10 more people walk in, they pick up a ball, right? There's always an electron for a person. There's always a ball for a person. There's always an electron for an atom. It's just that they're always moving, right? Okay, so at the lattice positions, you see there are positive ions. The reason why they're positive ions is because their valence electron has been removed. Where did their valence electron go? They're moving around. So each one of these is a positive ion, and the electrons are flowing throughout. So, because the electrons are moving, that causes one of metal's most primary characteristics. Metals are conductors in all states, solid, liquid. I mean, I guess gas too, but you don't really see metals in gases. So metals conduct very, very well. We talked about the requirements for conductivity. Anybody remember? There's 2 requirements in order for something to conduct electricity. It was a little while ago. So. In order to conduct, there's 2 requirements that had to be met. 1, it had to be charged. 2, the particles had to be moving. Look at these electrons. Are these electrons charged? Well, yes, they're electrons. Are they moving? Yes, they are. Metals conduct electricity very well. There was a kid in my 7th grade science class who learned this very well. At our lab stations, they had outlets. And so one day he stuck a fork into the outlet, and he learned about conductivity that day. Right? He also, there's some smoking smells coming from the outlet, and the teacher yelled at him a little bit, but he definitely learned what it means to conduct. Okay? So, how do you know if something's a metal? Come on. You know if something's a metal. Left of the staircase. Metals are shiny. We talked about this before, right? They look shiny. They have, the melting points. Their melting points can range from low to high. Some are low, some are high. Right? Some are so low that they already exist as a liquid at room temperature. What is that? What metal is a liquid? Yeah, Jason. Mercury. Mercury is a liquid already, right? This is gallium. Gallium is in the family of aluminum, right? It's underneath it. Gallium's melting point is the same as body temperature. So your body temperature is 98.6 degrees Fahrenheit, which in Celsius is about 38 degrees Celsius, right? So looks like a little metal bead, but if someone were to hold it in their palm, just close their palm on it and let it slowly absorb their body heat, this will turn into a liquid. Who's got warm hands? Chris? Let's see. Oh yeah, oh jeez. All right, so just let's say you don't have to squeeze hard. Just close it so your fingertips are on it. Right? And then like in 4 minutes we're gonna come check up on it. All right? So just don't turn it over because it's hard to get off the floor if it's okay. Metals are also, they vary from hard to soft. There are some metals that are soft, like gold. Right? Have you ever seen a Western where, somebody buys something in gold and they bite the coin? If they can see their teeth imprinted in the coin, then that's a sign to them that it's real gold. Right? Because that's what gold is supposed to do, because it's soft. Whereas if they didn't, then they pull out the gun, they shoot the guy, because he's like trying to pull one over on him, right? You don't make jewelry out of pure gold because it would get dented too easily. So you actually melt it down, you add silver, and then we call it like, 14 karat gold or 18 karat gold or 24 karat gold, right? Depending on the ratio of gold to silver, that's what gets a different carat rating. So, all right, anyways, the primary characteristic about metals, non-localized electrons, and how well they conduct and that they're shiny. Right? Because we can't say they're really hard because they're not all really hard. We can't say that they have high melting points because they don't all have high melting points. But we do know that they always conduct. and that they are shiny. All right. And with that, we're going to stop this here.